made this project possible. First is our Westchester University team. I'm going to be talking a little bit about Catherine Dowling. She's our master's student who's working hard on this project. I'll be going into her work in a little bit. Dr. Daria Nicotina, who's a professor of geology at Westchester. Dr. Young-Hoon Kim, he's an oceanographer at Westchester University. And then our field school students from the years 2019 and 2021. 2020 was a bust because of COVID. We weren't permitted to go out, but I did get special permission for us in 2021. And I'm going to emphasize some of the work that the field school students had been doing over those couple of years. And then the collaborators and the facilitators that really helped make our work possible, which is special thanks to Dr. Greg Latanze, Dr. Kate Markopole, Tony McNichol, Nathan Figley, Sandy Cowan, and then our sponsors who provided funding and resources, which is National Geographic Explorers Grant and Westchester University, various departments, and our College of Sciences and Mathematics. So the field school is something that we run at Westchester University every year, but it's not until this project got going that it became so heavily interdisciplinary. As I mentioned, our field school was out at the project I'm going to talk to you about in a minute in 2019 and 2021. And over those years has involved both graduate and undergraduate students from Westchester University, but also from the Indiana University of Pennsylvania, Slippery Rock, and Temple University. And those students have all come from the departments of anthropology, biology, English, geography, and geology. And I think I've covered them all. And the second from the left here on the far photo is Katie Dowling, the one who's doing her master's thesis on a more intensive study of what I'm going to be discussing tonight. Hopefully that'll be forthcoming soon. So a little bit of an overview of some of the field school research activities that I'm going to mention. We've been engaged in archaeological survey and excavation. We've utilized remote sensing, specifically through ground penetrating radar and sediment coring in marsh sediments in the field. In the lab, so to speak, or in the desktop applications, we've also applied probabilistic sea level models, storm surge models, and done some shoreline reconstructions. And we'll bring that a little bit together tonight. The general location of where we're working for this particular project, we're actually working along both sides of the entire bay. And we have a large overview study that hopefully will be coming out in publication soon this fall, if we're lucky, if everything goes well. We've got a couple of case studies within that bigger project, and one of them is right here along the Maurice River Neck area that I'm going to be talking about tonight. So our general location is shown here, and you can see sort of the environment right there over to the left, and that really does show some of the current shoreline erosion that's occurring down at the head of this peninsula here. Cultural resources along this Maurice River Neck have been explored for quite some time now, beginning back with Dorothy Cross's Indian survey. She was out in this Maurice River Neck, East Point area back in the late 1930s and into the 1940s. Alan Mounier did a master's thesis on a couple of sites out in this neck of the woods. Bill Liebknecht had a project down by the lighthouse that he undertook, and the Pinelands Archaeological Survey has been out there. So there's been, good background of cultural resources, documentation, and research that's been going on for quite some time now. And so you see the overview of the resources in that generalized location that I just showed you range from late Paleo-Indian / early Archaic through the 19th century, and include the entire range of indigenous pre-colonial settlement eras, all the way through the late woodland and possibly even to the contact era, as well as the lighthouse, which is a iconic feature of this part of the landscape, and some other historic archaeological resources. I highlight here one that I'm going to mention in just a minute. You'll see we have a couple of sites that I've pulled out from this region as examples of the cultural resources that are present, and then WCU survey 2019 and 21 includes some contributions that we've made to that particular area through our field school studies. And one is to put forth a radiocarbon date from a buried feature dating us to the late woodland. So some of the work that our students have been doing involve typical archaeological survey and test unit excavation across this dune landscape that really is characteristic of the area down in the far reaches of the peninsula. See the very sandy soils, but also based on work that had been done by Meunier and work that we had done later on here, indicates a number of different shell deposits, cultural shell deposits that are buried beneath layers of soil matrix. Oops, okay, there we go. Okay, and you'll see here some of the findings that have come from our excavations. Another feature here that is indicated in one of our test units, this one has not yet been dated, but we do have materials that we hope to date and add to that first radiocarbon date that we were able to obtain from the burned wood context. We have pottery, a number of different types of pottery, particularly spanning the early and the late woodland periods, and then a large amount of tortoise shell fragments, terrapin shell fragments, faunal remains, particularly from deer. And I have to thank, at this point, Dr. Moore from the Virginia Museum with her assistance with the identification of the faunal remains. That's not my specialization, but she was able to help out and let us know what we were actually finding through these different excavation contexts. Ground penetrating radar was brought out, and in the same places where our test excavation survey was laid out, we laid out several grids of ground penetrating radar grids and collected remote sensing data across these grids. 4 of our 5 grids indicate anomalies that we are now further exploring. We're working with geophysicists, particularly a geophysicist from Temple University, who has a great deal of experience working in these sandy sediments and with these buried matrices. We are pretty sure we have indicators of buried shell deposits, but are working to sort of confirm that by comparison to other remote sensing data that have been collected from other areas that we might be able to match with. One of the things that we're interested in looking at with these shell deposits is the nature of the shell deposits, and if they are changing over time. Do we have a lot of smaller ones that are then, or do we have, instead fewer larger ones? What's the nature of the cultural shell deposits out there? So the students got a good deal of training. All of our students who run the ground penetrating radar get their training from GSSI, because that is the supplier for our equipment. They get trained on how to lay out the grids and run the instrument, but also on the interpretive software, which is the big trick, is how to run the interpretive software. So we're hoping to continue this work, and you'll hear more in Katie Dowling's thesis about that too. Also, we've done a good deal of sediment coring in the marshes. So you see in this golf bag there, that is what our students haul out into the marsh. Those are all of the coring instruments. We can just keep adding on longer and longer sort of arms to make the coring instrument, go deeper and deeper. So this was our 2021 field school. We were plagued by, the rules of the university that we were only allowed to run a field school if we wore masks even outdoors. So we did, and you could see our student on the left complying with that, but also the tremendous amount of insects, particularly flies. So this helped with that too. So this is our coring instrument. It's a hand-driven Russian auger that we use to collect these sediment cores. Katie Dowling is again here collecting a core sample. We recorded all of the sediment information in the field. We didn't take the cores back to the university. We did all of our sediment core recordation in the field, and then left the sediment itself right there in the field, rather than storing it on campus. So we have all of these yellow codes are showing the location of our sediment cores, and we constructed several. So we have a dune. If you can follow my cursor, we have a dune, one of our dunes that run right across here. This is where we've been conducting our archaeological survey and excavation, and then cross-cutting that dune with our sediment coring so that we have these transects. We have a number of these transects. Only one of them is shown over here on the right as an example of how we reconstructed those one of the transects. So this is transect 2, and you can see there's a little bit of vertical exaggeration, making the dune seem much taller than it is. But some of the things that are indicated here, not so much on this particular transect, are the differences between the high marsh and the low marsh environment. The dune itself buried beneath marsh sediment accretion, and then in some cases across some of these transects, the presence of paleosols, which may be an indicator of, in some cases, of buried sites, buried cultural resources. So I'm only bringing one up here because this is really just the trailer for the whole project. They're all will be published out in Katie Dowling's thesis, all of our transects across the dunes that we've constructed. And you can see here that our sediments go down until we hit the dune sand, and then we're just going back. This is one of our shallowest transects. So we're just reconstructing the landscape back over several hundreds of years, not thousands in this particular case. In the lab or in a desktop application, we've been applying the probabilistic sea level projections based on the model generated by Kopp and colleagues from Rutgers University. And this is based on the IPPC recommendations to use the representative concentration pathways tied into localized datum. We used localized tide gauges, and you can see in the map over here to the right the tide gauges. So we're tying in our sea level projections to the Cape May tide gauge and also the Shipjohn Shoal tide gauge. And we can use that to generate a series of scenarios based on high, intermediate, or low probability for sea levels. We selected the years 2030, 2050, 2080, and 2100. 2100 is the farthermost range that these projections can be taken. Any slice of time at the decade level can be generated in between, but it's a tremendous amount of work. So we picked just these benchmarks or these points to model. And so we can see here, we have an animated version of the sea levels at various locations at our case studies along the Delaware Bay. I'm not running those animations, but if somebody's interested in seeing those animations up close, send me an email and we can talk about that. But these are the projections for the Delaware Bay. And you can see down here that this is a work under review right now that'll hopefully be coming out for everybody later. We also apply the sea, lake, and overland surges from hurricanes, otherwise known as the SLOSH model. This is a computerized model developed by the National Weather Service to estimate storm surge heights. It's based on a lot of historical information to generate predictions. For our simulations, we used historical hurricane data from the years 1878, 1903, 2011, and 2012. And it involves simulating different sort of wind approaches and a number of other factors. Again, we have detailed outputs from the SLOSH model. If anybody's interested in talking to me more about the detailed outputs from the SLOSH model for the Maurice River Neck or anywhere else in the Bay, just send me an email and we can talk about that at a later time. So these are the storm surges that were projected from the outputs. These simulations were done by our colleague, Dr. Young-Hoon Kim. He's an oceanographer in the Department of Earth and Space Sciences at Westchester University. And these are the low, intermediate, and high projections that match the sea level rise projections. And so we can see here that there are a number of different outcomes. But the takeaway from this is that the storm surges are really something to keep an eye on in the near term, more so than the sea levels, especially because the dune system is so non-existent in many locations along the bay and offering no protection for any kind of cultural resource behind them. We also have done shoreline monitoring and shoreline reconstruction. So you can see we've gone out several times, 4 times, I think, and recorded high and low tide data along the point there on the East Point Peninsula. We've got a high tide and a low tide. And we have that overlain here with our historical shoreline information. So we collected the shoreline information from imagery from 1930 all the way up to 2017, and then we added 2012. I think we added 2017, 2019, 2021, and then 2022, which we also have, has been added. And based on this, our graduate student has done some preliminary presentations at other conferences and has noted that up to about 289 meters of shoreline have been lost in some locations along this point of the peninsula there. So one of the icons of this peninsula, the East Point Peninsula, is the East Point Lighthouse. Preservation New Jersey has listed the East Point Lighthouse, also known as the Maurice River Lighthouse, as one of the most threatened cultural resources in the state. Built in the mid-19th century, it's the second oldest lighthouse in the state, and it's listed on the National Register of Historic Places. The recent work by Liebken et al. Is what was done to expand that National Register listing to create a National Register district that encompasses the lighthouse and some of the other cultural resources down at the far end of that East Point Peninsula. So following the impacts from a recent nor'easter in 2018, the New Jersey Department of Environmental Protection, along with some of their other collaborators, acquired resources or generated the resources to install a 900-foot geotube to protect the light from erosion and storm surges. And I think you can see this is prior to the geotube being installed. There's the sandbag operation that was there up until 2020 to sort of protect that resource. And then we have here the 2019 lighthouse sandbagging operation. And then the 2021, when we went back, the geotube operation down here on the far, on the bottom right-hand side. So it's pretty extensive, but given the storm surge projections, actually not sufficient to protect the resources that are on the backside of that that constructed dune, that artificially constructed dune. One of the things that we noticed while we were out there, my students were horrified, they couldn't take it, was on a section of this geotube is large boulder riprap. I think there had been maybe a boat launch or something like that that was riprapped, and the as one section of the geotube that hadn't been there in 2019, and just the impact on the wildlife that had with this bottlenecking and trapping of the horseshoe crabs. So they spent a good several hours one morning. I couldn't get them unfixated on trying to rescue all the horseshoe crabs. So I'm going to bring that up in the conclusions here. When I say the Maurice River Neck and East Point Peninsula contains the full spectrum of human occupations in terms of time periods. ranging from late Paleo to early late woodland, possibly into the contact era, and including 19th and early 20th century. Coastal erosion and storm surges pose near-term threats to both the natural and cultural landscape, and the sea levels are something that need to be kept an eye on for longer-term threats to those resources. Mitigation solutions such as the geotubing that I just showed should be also cautiously monitored for latent or unanticipated impacts on both cultural and natural resources.